Hello and welcome to Math 270 Linear Algebra here at Cañada College. My name is Lapuz. In this video we will take a quick look at the least squares problem. So our least squares problem will get us to a system of linear equations which can be possibly written as an AX equals B with matrices, but there will be a good chance that it will be inconsistent or we will have no solutions. So instead of dealing with this AX equals B, what we might be interested in is this AX equal to 0 portion and see if we can minimize that and minimize the distance between B, the vector B, and the vector that we get from A times X. So from a theorem, we can take a look at this as a projection of B onto S, where S is our vector space, and S happens to be the row space, or the column space, excuse me, it's the column space of A. So an orthogonal projection from B onto the column space of A would be what we would look at. And what we want to do is we would want to figure out what that is. And so by subtracting this B and the projection of B onto A, what we'll get is something that is perpendicular to the column space of A, which happens to be the null space of A, as we learned the column space of A and null space of A transpose. Sorry, that's a null space of A transpose. Our direct sums, or they would be the direct sum of those two, will add up to Rm. So what we want to do is, being that AX minus B is in the null space of AT, we're interested in solving for this equation now, where we apply A of t and then we put this AX equals or AX minus B in there and get the null space. Now if we take a look at this equation, we can distribute the A transpose and we get A transpose times X and then A transpose times B, and the difference between that should be equal to 0. Another way to look at it is we can solve for, we can put the A transpose times B on the other side, and then we have A transpose times A. It's going to be a new matrix, and then times your unknown variable X should equal to A transpose times B. And now this should have a solution because we noted that A times X minus B is in the null space of A of t, so then that would necessarily make this equation true. Okay? So that's the general idea behind the least squares problem and how it relates to orthogonal projection, orthogonal subspaces, and our basic subspaces of our matrices. So we're going to set up our equation this way using the least squares method. What we're going to be given are a bunch of points. Like in statistics, we have a bunch of data points that we would plot on an xy plane. And then if we're dealing with linear equations, our linear equation would be y is equal to c sub 0 plus c sub 1 times x. And from there, you can rewrite this with these equations to have this as an a, and then this is an x, the unknown c1, c2, or c not c1 variable, and then your y values for your b. Same for the quadratic. Your quadratic equation would look like this. So these are going to be your a values and your b values. So let's attempt this problem where we're looking for the least squares using quadratic polynomials using these particular data points. So what I'll do is I'll set up the system of equations, and then from there be able to draw out these matrices and then set up their matrix equation, and then use this equation to eventually solve for it. Okay, So given our quadratic formula, or our quadratic equation, we would expect an equation that looks like y is equal to c sub 0 plus c sub 1 times x plus c sub 2 times x squared. And so we would be interested in looking for c sub 1, c sub 2, or c sub 0, c sub 1, c sub 2. Now, by putting these points into the equation, I will get, for the first one, a 6 is equal to c sub 0 plus c sub 1 times negative 2 plus c sub 2 times negative 2 squared. And going on down the line, I'll get a 5 c sub 0 plus c sub 1 times x, which is negative 1, plus c sub 2 times negative 1 squared. And then we'll get a 7 halves is equal to c sub 0 plus c sub 1 times 0 plus c sub 2 times 0 squared. And then a 2 c sub 0 plus c sub 1 times 1 plus c sub 2 times 1 squared. And finally, negative 1 is equal to c sub 0 plus c sub 1 times 2 plus c sub 2 times 2 squared. Now, let me just rewrite it to actually make it look like a system of linear equations. And I will write the c sub 1 values, or c sub 0, and then I have a minus 2 c sub 1, and then a plus 4 c sub 2, and this is equal to 6. And then we'll go on and do the rest of them. And that one's equal to 5, and then c sub 0, and then we have a bunch of zeros, and you get 7 halves. And then c sub 0 plus c sub 1 plus c sub 2, and this is equal to 2. And finally, c sub 0 plus 2 c sub 1 plus 4 c sub 2 is equal to negative 1. And continuing on, we can look at the matrix of coefficients. We have 1s all the way down here for the 5 equations. And then we have the x values, that's negative 2, negative 1, 0, 1, and 2. And then the x squared values, that's 4, 1, 0, 1, and 4. So that's kind of like what we saw here, anticipated here in our set of equations. And this will have c sub 0, c sub 1, c sub 2 being multiplied to it, and our b will end up just being the y values, which is 6, 5, 7 halves, 2, and negative 1. Okay. So in order to solve for this, if we're identifying these as your A, and then your X, and then your B, what we're going to be interested in looking for is A transpose, and then we'll take that A transpose multiplied by A, and then we're going to set that equal to A transpose times B. So we'll eventually get this thing, which is going to be a matrix. And if we look at this matrix A, it's a 5 by 3, and then A transpose is 3 by 5. So we got a 3 by 5 times a 5 by 3. And we're going to end up with a 3 by 3 matrix. And this is a 3 vector. Your X is a 3 vector. And again, this is a 3 by 5, and then B is a 5 by 1. And so we're going to get a 3 by 1 vector. And so we get a matrix times a vector, and then that's it. Okay, and so from here, what I'm going to do is I'm going to call on Python to help me get through these values. And we've got our stuff imported, and we'll go down to the actual problem that we're working on. So first of all, we want to identify the matrix. Here is our matrix with the 1s, the x values, and then the x squared values. And then your B matrix is going to be the set of y values. So that's the beginning of the problem. Now that we have this, we will multiply A transpose times A to get the matrix that we're interested in. And so again, we're expecting this 3 by 3 matrix. So that's 5, 0, 10. So let's get that written down here. We're going to get a 5, 0, 10. There's a 10 here and a 10 here, and I believe these are zeros. Let me double check. Oh, it's 35 for that last slot. And then now we have this x over here, and we want to set this equal to some 3 or 1, yes, a 3 by 1 matrix. And so that would be this next step. So it's 15.5, negative 17, and 27. So 15.5, negative 17, and 27. So now we're just solving for this linear equation, which should have a solution, should be consistent. And for that, I would probably be interested in just augmenting it. 5, 0, 10, and 15.5, 0, 10, 0, and a negative 17, and a 10, 0, 35, and 27. Okay, and then a quick RREF on the computer. And we should get our solution. And the way I'm going to do that in Python is I'm going to first combine the two matrices just by inserting that column, that last column at the end, and then we'll do an RREF. Seems like I get some fractions and I get some decimals. I'll take that, doesn't matter. That's our result that we're interested in. So let's get that copied. And we have our values, our C1, C2, or C0, C1, C2. And so this is it. This is C0, this is C1, and this is C2. Okay, so if you take your polynomial y equals 3.67-ish minus 17 tenths times x minus 0.0257 times x squared, you should see that fit your problem. And I think I have a quick graph of that in Desmos, so let's open that up. And here we start off with our set of points. And then this is the polynomial that we just got. And so if we graph that polynomial, we'll see that it's the second order polynomial that would best fit the data set. Okay? All right. So I hope that helps, and good luck with your work.